As you reach this point in the course, it becomes less about learning one more technique and more about learning how to keep your work honest when the pressure is on to ship a model quickly. Many beginners discover that the hardest part of data AI is not building a model that looks good in a clean experiment, but building a model that keeps working when the real world is messy, incomplete, and constantly changing. The 3 traps in today's title are common because they rarely look dramatic while you are building, and they often reveal themselves only after a model has already gained trust. Data leakage creates an illusion of intelligence by letting the model see information it should not have. Label noise teaches the model the wrong lessons, even when your pipeline is perfect, and cold start realities remind you that many systems fail simply because there is not enough history to support the promise you want to make. This is the final episode in this sequence of titles, and the goal is to leave you with a practical mindset that helps you avoid shipping a model that succeeds on paper but fails in use. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. To keep the conversation grounded, it helps to start with a simple definition of what a trap is in this context, because these are not exotic edge cases reserved for advanced projects. A trap is a situation where your model appears to learn a meaningful pattern, but the pattern is actually an artifact of how the data was created, labeled, or split, rather than a stable relationship that will exist when the model is used. This matters in cloud and security-adjacent analytics because operational data is full of process signals, such as what gets logged, what gets reviewed, and what gets recorded after an incident, and those process signals can masquerade as predictive features. A beginner might think the model discovered a deep insight when it actually learned the footprint of your investigation workflow. Traps also matter because they are contagious. Once you trust one misleading result, you design the next step around it, and the project can drift far away from reality. Avoiding traps is not pessimism. It is how you protect your time, your credibility, and the people who will rely on the system. Data leakage is the first trap because it is the fastest way to create a model that looks amazing and is completely unusable in production. Leakage happens when the model receives information, directly or indirectly, that would not be available at the moment you intend to make the prediction. That can be as obvious as including a field that is only filled in after a case is resolved, but it is more often subtle, like a feature computed using a time window that stretches past the prediction point. Leakage can also occur through the way you split data, such as mixing future records into training in a time-dependent problem, or splitting repeated entities so the model sees the same user patterns in both training and testing. The dangerous thing about leakage is that it rewards you immediately with high scores, so it feels like success, and that feeling can discourage deeper investigation. Once you accept leaked performance as real, you build confidence around a model that is not actually learning the task you care about. A useful mental discipline for spotting leakage is to imagine a strict timeline and then force every feature to pass a simple test. Would this value exist at decision time? And would a system making the decision truly know it? This test is not about whether the value is stored somewhere in your database. It is about whether the value would be available without hindsight. Many leakage cases come from features that are technically present in the dataset, but were populated only after the outcome occurred, such as flags added by a human review or fields updated during remediation. Another common leakage source is aggregation that accidentally uses future behavior, like computing a customer's average behavior across a month and using it to predict an event that happened in the middle of that month. In cloud environments, where logs are often backfilled and normalized, it is also easy to leak through timestamps and batch processing artifacts that correlate with outcomes. The timeline test forces you to separate what you know now from what you would have known then, which is the heart of leakage prevention. Leakage also hides inside modeling convenience steps that beginners treat as harmless preprocessing, which is why disciplined evaluation is inseparable from leakage control. If you normalize or standardize using the full dataset, you have allowed information from evaluation data to influence training, which can inflate results in small but meaningful ways. If you select features based on their correlation with the target using all rows, You have directly used the answers from your evaluation set to decide what the model is allowed to see. If you build encodings that depend on the target, such as target encoding, and you compute them without carefully separating training from evaluation, you can create a feature that is partially made of the label itself. The pattern across these examples is the same. You are using information from the future relative to the training process, even if you never intended to. The safest way to think about it is that anything that learns from data must be learned using only the training portion of data, and then applied unchanged to whatever you call validation and testing. When that discipline is in place, leakage becomes much harder to accidentally introduce. Even when you avoid leakage, label noise can quietly cap performance and can distort model behavior in ways that look like algorithmic flaws but are actually data truth problems. Label noise means your target values are sometimes wrong, inconsistent, or incomplete relative to the real world you are trying to model. In many operational datasets, labels are not a direct measurement. They are a record of a decision made by people and systems, and those decisions have gaps. A benign event might be mislabeled as suspicious because it was investigated during a stressful incident, and a truly suspicious event might be labeled benign because nobody noticed it. Some labels are delayed, meaning the truth becomes known only after time passes, and some labels are biased toward what is easy to detect rather than what is truly happening. In security-relevant workflows, labels often reflect triage capacity, meaning what gets investigated gets labeled, and what is ignored stays unlabeled or defaults to benign. A model trained on such labels can become a mirror of investigation behavior rather than a detector of underlying risk. A beginner-friendly way to see the impact of label noise is to imagine trying to learn a rule from a teacher who sometimes marks correct answers as wrong and wrong answers as correct. If that inconsistency is rare, you can still learn, but you will always feel a ceiling because some contradictions cannot be resolved. If the inconsistency is common, you may learn the wrong rule entirely, especially if the incorrect labels cluster in particular segments. This is why label noise is not just random static. It can have structure, such as one team labeling more aggressively than another, or one time period having poorer labeling due to a tooling change. Label noise can also create false confidence if your evaluation shares the same noise patterns, because the model can learn to match the noisy labeling process rather than the underlying phenomenon. In other words, you can get a high score for agreeing with imperfect labels, even if the model would fail when judged against real ground truth. Understanding this helps you interpret results with humility and prevents you from blaming the algorithm for a problem that is really in the target definition. Handling label noise well starts with being precise about what your label represents, because many projects fail by assuming the label is a clean statement of truth when it is actually a proxy. If your label is based on a human decision, then what you are modeling is the human decision process unless you have evidence that the decision consistently tracks the underlying truth. If your label is based on an alert, then you are modeling alert logic and alert coverage, not necessarily the true presence of malicious activity or system failure. This is not inherently bad, but it must be acknowledged because it changes what success means. If you want to predict whether something will be investigated, then an investigation-derived label is appropriate. But if you want to predict whether something is actually harmful, you need a label that tracks harm, which is harder. A responsible workflow often includes auditing label definitions, checking disagreement rates, and looking for segments where labels behave differently, because those segments are where the model will learn inconsistent rules. When you treat labels as a design choice rather than a given fact, you gain the ability to improve them and to set realistic expectations. Another important label noise trap is that it can interact with class imbalance in a way that makes minority detection especially fragile. If the positive class is rare and some positive labels are missing or wrong, the model may never see enough clean examples to learn the difference between true positives and hard negatives. This can produce a model that either ignores the rare class or becomes overly aggressive because it cannot find stable boundaries. In cloud operations, where incidents are rare but costly, the label set may be created from incident reports, and those reports may vary in completeness depending on team maturity and tooling. That means your ground truth might be stronger for some systems than others, and the model might learn unevenly. A careful approach is to treat label noise as a reason to invest in better data processes, not as a reason to endlessly tune hyperparameters. If you keep trying to squeeze performance out of a noisy label, you may simply teach the model to fit the noise more cleverly. The right instinct is to improve the target signal first, then optimize the model. Cold start realities form the third trap, and they are often overlooked because they are not a data flaw so much as a product reality. A cold start happens when you need to make predictions for a new entity, like a new user, a new customer, a new device, or a new product, but you have little or no historical data for that entity. Many models quietly rely on patterns learned from history, such as behavior over the last week or frequency of prior events, and cold start entities have none of that. Beginners often assume the model will just generalize, but if the strongest features are history-based, the model's confidence and accuracy can collapse exactly when the system first needs to make decisions. This is common in recommendation systems, anomaly detection for new services, and risk scoring for newly created accounts. In a cloud security context, new accounts and new workloads appear constantly, and attackers may specifically target the earliest moments when monitoring is weakest. Cold start is therefore not a minor inconvenience. It is a predictable and recurring condition that must be planned for. A practical way to think about cold start is to separate identity-based history from context-based information, because cold start is mostly the absence of identity history. Even if you do not know how a new user behaves, you might know the context, such as the environment, the region, the device type, the time, or the onboarding path, and those context signals can support reasonable early decisions. Cold start planning often involves designing features that do not require long history, such as short window counts, immediately available profile attributes, or aggregate statistics at a higher level that are not tied to one entity. It also involves making peace with uncertainty, meaning you may need to treat early predictions as lower confidence and handle them with different thresholds or workflows. Beginners sometimes try to solve cold start by forcing the model to make strong predictions anyway, but that often increases false positives or false negatives because the model is guessing without evidence. A safer approach is to explicitly recognize cold start cases and design the system's behavior to be conservative, staged, or supported by rules during the earliest period. That is not giving up. It is aligning the decision policy with the evidence available. Cold start also connects back to evaluation, because if you do not test cold start scenarios, you can ship a model that performs well in the aggregate while failing for the newest, most operationally important entities. This failure mode happens when evaluation data includes entities that already have rich histories, so the model benefits from history-based features and the score looks strong. Then in production, new entities appear every day, and the model's performance for those cases is far worse than the headline number suggested. A responsible evaluation strategy includes entity-based splits or time-based slices that simulate onboarding, so you can see how performance changes when history is limited. It also means checking performance as a function of entity age, like how well the model performs on day 1 versus day 30. In many real systems, the model's job is hardest at the beginning because uncertainty is highest, and that is exactly where you want to know how it behaves. When you incorporate cold start evaluation, you stop treating it as an afterthought and start treating it as a core requirement. These three traps also interact in ways that can make a project feel haunted if you do not recognize the connections. Leakage can make cold start performance look great in development if your features accidentally include future information that would never exist for a new entity at decision time. Label noise can be worse for cold start entities if they are investigated less often or labeled less consistently, which means the model learns less reliable rules for exactly the cases that have the least data. Leakage can also amplify label noise because the model can learn to exploit inconsistent labeling artifacts, producing a brittle system that matches yesterday's workflow quirks instead of tomorrow's reality. This is why the healthiest mindset is to treat modeling as a chain where each link must be trustworthy. Feature availability must be honest, labels must be meaningful, and deployment conditions like cold start must be planned for. If you fix only one trap and ignore the others, you may still ship a system that surprises you later. Seeing the interactions early helps you debug faster and prevents you from attributing every failure to the algorithm. A final set of habits can keep you safe across all three traps without requiring you to become overly technical, because the core is disciplined thinking rather than fancy tools. For leakage, you keep a strict prediction time mindset, document when each feature becomes known, and enforce training only fitting for every transformation and selection step. For label noise, you treat the target definition as a first-class design decision, audit label consistency where you can, and interpret performance in light of how labels are generated. For cold start, you test explicitly for new entity conditions, design features that do not rely solely on long histories, and build decision policies that respect uncertainty early in an entity's life. The thread running through these habits is realism. You do not let your dataset pretend to be the world. You constantly ask how the world produced the dataset. In cloud and security settings, where data is operational exhaust rather than a carefully designed experiment, that realism is the difference between a model that earns trust and a model that creates churn and skepticism. When you adopt these habits, you also become faster because you spend less time chasing phantom improvements that were never real. As you close this part of the course, the most valuable takeaway is that strong data AI work is less about cleverness and more about integrity in the pipeline from reality to prediction. Data leakage is a trap because it gives the model forbidden hindsight and inflates evaluation. Label noise is a trap because it teaches inconsistent lessons even when training is flawless. And cold start realities are a trap because many systems demand predictions precisely when the least evidence exists. You do not avoid these traps by memorizing rules. You avoid them by practicing a consistent mental model of time, availability, and meaning, and by designing evaluation to reflect how the system will actually be used. If you keep that mindset, your models will be more stable, your results will be more reproducible, and your explanations will feel grounded rather than defensive. Most importantly, you will build systems that behave responsibly when the environment shifts, when labels are imperfect, and when new entities appear without warning, which is exactly what real operational data demands.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.